The Earth's crust contains many compounds, but the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide. Split the aluminium from the oxygen and you have one of the world's most useful metals. You can split a compound using electricity. The idea is to pass an electric current through it, a process known as electrolysis. A circuit is set up using 2 carbon electrodes, an ammeter and a power supply. The white powder is lead bromide. Switch on the power supply and nothing happens. The ammeter reads 0. Solid lead bromide doesn't conduct electricity. It needs to be molten. Lead bromide melts at 370 degrees Celsius. Switch on now and a current flows. In this circuit, the electrode on the right is positive, the one on the left is negative. As electricity passes through the molten lead bromide, chemical reactions start. On the left, at the negative electrode, nothing appears to be happening. But at the positive, bubbles mean a gas is being produced. Placing small tubes around the electrodes traps any gas, making it easier to see their colour. What could the brown gas be? The gas is bromine. Although nothing obvious appears to be happening at the left-hand electrode, pouring the molten lead bromide away reveals a small silvery metallic bead. This is pure lead. So, passing an electric current through molten lead bromide breaks it down into the elements lead and bromine. To work out why this happens, imagine you can see the charged particles, the ions, in the compound. There are positive lead ions and negative bromide ions. Once the power supply is switched on, the lead ions are attracted to the negative electrode. The bromide ions are attracted to the positive electrode. Lead ions pick up electrons. They lose their positive charge and form lead atoms. Bromide ions give up electrons. They lose their negative charge and become bromine atoms. These form a gas. Electrolysis of lead bromide only works when the compound is molten. Why doesn't it work when the compound is solid? Change the compound from lead bromide to zinc chloride and the products of electrolysis will be different. What would you expect to see happening when electricity is passed through molten zinc chloride? This time, bubbles of a very pale gas appear at the positive electrode. It turns damp blue litmus paper red and bleaches it lighter. So what gas is it likely to be? Again, nothing appears to be happening at the negative electrode on the left. But pouring off the molten zinc chloride reveals a bead of pure zinc. In industry, electrolysis is carried out on a huge scale. Massive amounts of electricity are used to extract reactive metals, like aluminium, from their ore. chloride is one of the world's cheapest and most widely available raw materials. It's found as rock salt in vast deposits underground, and it's dissolved in all the oceans of the world. The electrolysis of sodium chloride solution is an important industrial process. Mix the salt with water, pass an electric current through it, and a variety of useful substances are produced. To work out what's going on, here's a much simpler setup in the lab. 2 electrodes immersed in sodium chloride solution are connected to a power supply. The electrodes are made of carbon. They're supported by an insulated hook. See what happens when an electric current is passed through the solution. What evidence is there that chemical reactions are taking place? Bubbles appear around both electrodes, a sign that gases are being produced. To collect the gases, a test tube full of sodium chloride solution is placed over each electrode. Gas displaces the solution and collects in the top of the tube. So, what are the gases? Both are either very pale or colourless, but they can be identified by simple tests. The gas collecting at the positive electrode is tested with damp blue litmus paper. It goes red and quickly bleaches white. The gas is chlorine. The gas collecting at the negative is tested with a lit splint. It pops, a sure sign that this gas is hydrogen. So, why does the electrolysis of sodium chloride solution produce hydrogen and chlorine? Imagine you can see the charged particles in solution. There are sodium ions, which are positive, and chloride ions, which are negative. The others are present in water, positive hydrogen ions and negative hydroxide ions. These different charged particles are all free to move. Once the power supply is switched on, the positive ions are attracted to the negative electrode. The negative ions move towards the positive. Sodium and hydrogen compete to gain electrons. The hydrogen ions win out. They lose their positive charge and form bubbles of hydrogen gas. Competition also happens at the positive electrode. This time, chloride ions win out, losing their negative charge and forming bubbles of chlorine gas. Industrially, the electrolysis of sodium chloride solution can provide us with many useful materials. Chlorine is used as a disinfectant in swimming pools. Hydrogen is used as rocket fuel. And the sodium hydroxide solution left behind is used in the manufacture of bleach. Electroplating is used to protect metals from corrosion and make articles more attractive. Copper plating is easy to set up in the laboratory. All you need is a solution of copper sulfate and a method of passing electricity through it. 2 carbon electrodes attached to a power supply are immersed in the solution. Switch on, reactions begin, and a current flows. On the left, at the positive electrode, bubbles appear. This colourless gas is oxygen. At the negative electrode, there are no bubbles, but the carbon is slowly starting to change colour. It's being coated with a layer of copper metal. Copper ions in the solution are attracted to the negative electrode. They react to form copper atoms and plate the surface of the carbon. It's the copper ions that give the solution its attractive blue colour. So, as they're gradually removed, what would happen to the solution? Change the electrodes to copper and different reactions occur. This time, nothing appears to happen at the positive electrode on the left. There are no bubbles, so oxygen isn't being produced. But at the negative electrode, the copper is beginning to change in appearance. To find out what's happening, we first need to weigh a new set of electrodes. This is going to be the positive electrode. It has a mass of 39.60 grams. The negative electrode has a mass of 39.61 grams. They're almost the same. 2 hours later, and reweighing provides some clues about what's happened. But first the electrodes need to be rinsed and dried. The negative is now 40.92 grams. It's heavier than it was before. The positive is 38.22 grams. This electrode is now lighter. To explain these changes, imagine you can see the particles in copper sulfate solution. There are positive copper ions and negative sulfate ions. Switch on the power supply and the copper ions are attracted to the negative electrode. The sulfate ions are attracted to the positive. The copper ions gain electrons. They lose their positive charge and form a deposit of copper atoms on the metal strip. At the other electrode, the negative sulfate ions don't react in any way. Instead, copper atoms in the metal strip become positively charged ions, which dissolve into the solution. While one electrode loses weight, the other gains it. To electroplate an object with copper, a similar setup can be used. The solution is still copper sulfate. The positive electrode is copper. But the negative electrode is now the object to be plated. After a few minutes, the spoon is plated with a good coating of copper. Increase the current and see what happens. A thicker layer of copper forms, but the plating is poor. It rubs off easily. The size of the current used during electroplating is crucial. Switch on now, and a current flows. In this circuit, the electrode on the right is positive, the one on the left is negative. As electricity passes through the molten lead bromide, chemical reactions start. On the left, at the negative electrode, nothing appears. The Earth's crust contains many compounds, but the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide. Split the aluminium from the oxygen and you have one of the world's most useful metals. You can split a compound using electricity. The idea is to pass an electric current through it, a process known as electrolysis. A circuit is set up using 2 carbon electrodes, an ammeter and a power supply. The white powder is lead bromide. Switch on the power supply and nothing happens. The ammeter reads 0. Solid lead bromide doesn't conduct electricity. It needs to be molten. Lead bromide melts at 370 degrees Celsius.